Hey, welcome everybody, and thanks for joining us for the third of our Unfiltered series. Again, here with my colleague Bryce. I'm John Marchant. Yeah, today I wanted to have a chat about manufacturing. Making stuff is a big part of what we do. Design is obviously a really major component of that as well. But we live in a time where manufacturing things has really changed, to be honest. It's not the preserve of massive companies and huge investment to take an idea for a product and turn it into something you can actually buy. And you see that across social media, across the internet. You see it in everyday life, that more and more people are able to say, I'm going to make something.
Yeah.
So what I wanted to look at first up is just some of the straightforward old-fashioned tech that's been used in the past, and then some of the ways we've kind of pushed past that. I think the thing people are most aware of, if you talk about getting something made, they think about CNC. They think about big machines milling chunks of metal. And it's probably, I think a lot of people see that as like one of the coolest things, because there's chips of metal flying everywhere, and it's sort of big and impressive. That is a good chunk of what we need, but I think the thing that for me was a learning curve when we were first working with this was that designing something in CAD and then getting it actually manufactured, actually running the machines or having someone run the machines, is a really they have to be very closely integrated for it to be done right. But a lot of the time, it's very easy for there to be a disconnect because it's different people doing different things, different software, different processes. I'm self-taught. Put that out there right at the beginning. I've not had formal training with this stuff. I've found my way, and that again is possible because of the advances in software that's available to us and that kind of thing. Let's wind it back one level. I have always thought that coming at this from the point of view of a designer, animator, somebody who's into creative media, 3D stuff's always scared me.
Always.
Yeah?
You're terrifying.
On the same page.
Absolutely terrifying.
Yeah. I've been using After Effects since it was knee high and so on. And the 2.5D aspect of animation, okay. But I know you feel the same, that it's like a whole separate skill set to start to work in a third dimension.
It's a separate skill set. It's a lot more computing power. It just becomes very confusing. So what is the basics of taking a product idea in your head and putting it down on paper but in 3D?
Yeah, well, honestly, the thing that I found that was a big switch for me was that the difference between 3D modeling for creative purposes and 3D modeling for CAD, which was the part that I was new to years back, was that all of a sudden everything was grounded in reality. If you start to model something, there's amazing free tools like Blender out there you can do huge amounts with, but it's really difficult to ground that in any kind of reality. You can create a plane, a blob, a shape, or something, and have it mean almost nothing. So you've got nothing to tie you to anything. And what actually really sort of gelled for me straight away once I was thinking, how do I get a product into reality, was all of a sudden we're working in real dimensions, real details, real world factors that had to be specific. And actually, one of the things that I found is, it's most common now if I need to work something new is I'll sit there with calipers and measurements and parts in hand and come up with core basic dimensions, things that define, okay, what's the the bounding box that I can work within? What's the overall size? What are the critical factors?
Yeah.
And what's really interesting is that when you start to sketch stuff in software driven by those dimensions, all of a sudden the aspect of working three-dimensionally is far, far easier. I'm very comfortable in CAD these days, and working three-dimensionally was conceptually always fine in my head, but never able to, I always felt like either navigating or manipulating the interface in the more creative 3D software left me cold. I was always lost as to where am I looking, what's going on, So that grounding in reality, really big deal. And I've got to obviously give a massive shout out to the guys behind Fusion, previously Fusion 360, just from the point of view that it may still have some complexity, and it's a fairly deep package, but being able to wrap everything inside one space so that you can cover everything from modeling to simulation to rendering to actually running machines, it's fantastic, and it means that we can collaborate with other people using the same software as well. And funnily enough, it's rolled over onto the other side. We're rendering pack shots of products directly in the same software that we're designing it in. So we see it on the creative output as well. But like I say, the core of it is driving it from dimensions, and that's without getting too techie about it. It's one of the things that Fusion is great at, is that you can create designs and sketches that are procedurally created from dimensions that you put in. Okay. It doesn't work for everything, and I have to admit I'm not always the best at saying, okay, let's work it that way. Sometimes I get a bit kind of, let's meld the clay. I'm going to just kind of futz around with it and work with something, and maybe that's not so procedural and clever, but in certain circumstances you can have a part and say, okay, well, I'm going to need 3 different versions of this, 5 different versions of this, and I can define it by a table of values and do all of the design work, and then say, yeah, great, now I need one that has 7 spokes instead of 5 and a different thread size and a different diameter.
Brilliant. Re-input
that same stuff and effectively have your work done for you. I sort of, on the creative side of things, I long for that kind of an effect in After Effects, for example. The closest you get is, some degree of templating, but being able to, use sort of global inputs to then say, okay, now give me all the work I did again. With a reflavor. That's really, really smart. I just wanted to jump into some physical stuff as well.
I've got a table full of
bits of shiny stuff here just to talk about.
Some of which I can work out what it is, some of which I've got
no idea. It. I know there's going to be things you recognise and things you don't.
Yeah, absolutely.
So I just wanted to talk about some of the tech, basically, and some of the reasons that we choose to do things the way that we do. So some example parts that are CNC milled aluminium, commonly people like to talk about, it being aerospace aluminium. Yes, it is, but there are a lot of different grades for different purposes. And this is the kind of thing that is, a solid billet of metal is cut away to produce a finished part with, potentially incredibly fine tolerances. You can get, this is a part straight off a machine. And you can see the surface finish straight after it's been cut. There's been no processing done on that. Obviously, the internal side that is not facing the customer, as it were, you can see tool marks. But it's possible to create, exceptionally high quality parts these days, straight from a CNC machine.
And to what level of precision are we talking here? Because all this relates to optics at the end of the day.
That's it, yeah. So the numbers get really small when we're talking about optics. So, for example, if we're shimming a lens, we take it down to, we're not talking millimeters, we're talking 0.01 of a millimeter. is the scale that we're working on for accurate back focus.
So how does that relate to other industries? Who else works to that precision?
Very few people do. It depends on the overall scale, because obviously precision is a function of scale. There's no point making a part for a bridge that is to the nearest 10 microns. But if you're creating really sub-miniature components, then a few microns is a big deal. That said, there's a general principle for CNC work of this kind of thing that people will work to plus or minus a tenth of a millimeter.
Right.
And that's a kind of a general engineering standard. There are a lot of standards like that are sort of accepted. If you say nothing else, that's what most engineers will infer for this sort of palm holdable, practical size part. Realistically though, in a lot of cases, although it doesn't apply to every dimension, there are lots of cases where that's not good enough.
Yes.
And fit and finish is one thing, but accuracy goes beyond that. But yeah, I mean, the repeatability of modern CNC mills is something else. It's really, you can these days get beautiful parts in relatively a straightforward manner. The problem is, of course, that when you mill something from a billet like that, it can be very wasteful to do it.
Yes.
So an example of a wasteful design, for example, would be something like this. If you imagine building a bounding box around that in 3 dimensions, we've milled away virtually everything. Now, fortunately, both practically and environmentally, aluminium is enormously recyclable. So it's not a major issue as such. But nonetheless, you're spending machine time on getting rid of something. And, intelligent methods of designing stuff obviously go a long way with that. Sometimes you need the rigidity and the simplicity of it's a single part made in one process. Sometimes you'd be far better off saying, you know what, it's much more efficient to bolt this thing together out of multiple pieces.
Yeah.
So yeah, that's a good example of what an efficient part might look like. But then equally, we also have examples of efficient machining or efficient methods of cutting stuff. So if I take a big chunky example of something here, a big old piece of metal. Literally,
I recognise that one from the front of our building.
Exactly, yeah, that's it. Literally, a spare one, a piece of logo off the front of our property here. Cutting a piece of material, once you get into this scale, you don't want to be milling this sort of thing unless there's a real need to. So choosing a method is really important. This is water jet cut. Water jets are amazing.
Water jet can cut through that thickness?
And plenty more besides. Yeah, water jets with abrasive are amazing tools. Relatively small kerf. It doesn't, cut a large amount away. You can have, as you can see, almost perfectly square internal corners as well, because you lose so little. But of course, it doesn't have anything like the precision that we need for most of the things we do. So it's as with all this stuff, it's a horses for courses thing. You pick a method that suits. I'll show you another example of making a choice. Now, obviously, these parts, there's a couple of differences here, but they are predominantly very similar to one another.
Yeah.
And this is a case of working out what do we really need. So this individual part had some requirements. It needed to be flat, it needed to be light, it needed to be accurate, it needed to be able to have glass bonded to it, it needed to have some other mechanical parts interface with it. Now, we tried 2 different approaches. One of them is enormously more expensive than the other. So this is laser cut and then folded and stamped into its shape.
Right.
Very scalable process, kind of thing you can do, either die cutting or laser cutting, and then folding a piece of sheet material costs next to nothing to do by comparison. This guy is CNC milled, and not just from 2 sides, but there's a 3rd axis hole required as well. and maintaining tolerances when you're milling very, very thin parts is really tough. So we've got a very expensive and a very cheap option. Of course, the world being the way that it is, you know which one of those ended up being a necessity. Yeah, of course. But it's a good example of how, it's both to our benefit and to the consumer's benefit to try and at least pursue the most efficient way of doing something.
Absolutely.
And I've got, in a more successful example of the same concept. There's a couple of components from inside a lens mount here, which
I would have no idea what that does.
Yeah, they effectively do the same job. They're retaining springs used behind a still type lens. And this is effectively a set of small springs attached to a laser cut part and stamped into shape. Very, very straightforward to do. This guy produced by a multi-axis milling process, very expensive. However, you can prototype this very easily. It's perfectly feasible to make one. Building a jig and a template and a tool to stamp something.
Yeah,
Very different.
one-off.
Yeah, that's it. And a lot of the time that sort of thing applies. The big buzzword obviously is 3D printing, and we do use 3D printing in a couple of different forms. But there's a good example where we've transitioned parts and stuff that we make. So this is just a little guide that we use. And
Guides that answers probably one of the most common questions we receive.
That's it. How much space is there? What lenses fit? If you buy a revolver, you get one of these in the box. Same with other stuff that we produce where there are limits involved. And we've made these in the past using various kinds of 3D printing because it's a relatively awkward shape with a fair degree of precision. It suits resin 3D printing quite well. But we also found a way to produce the same effect, geometrically speaking, from a much simpler folded piece of sheet material.
This one looks a lot more premium to me.
It's actually, this is the irony of it, is that a lot of the time, if you do it right, just because something is done in a more cost-effective way doesn't mean that it is worse. Sometimes it means you can pay more attention to what does the surface finish look like, what does the detail look like.
Yeah.
It's an interesting one where it is still about scale. I mean, the classic example, though, excuse me, knocking things over, for scale is once you get onto injection molding. Injection molding is a huge industry. The only thing huger is the size of the machines you need to do it. These are monster machines. And making a mold to do injection molding is a very expensive process. They can typically, start from $5,000 to $10,000 and go on from there, just to be able to turn out your first part. So for a very long time, the RF rear caps that we produced are actually done using a specialized 3D print process, and it's a material type that I think is actually becoming quite well known. This is made on an HP multi-jet fusion machine, which produces a really tough, robust, reliable 3D print. It has some limitations. There's limited colors, there's limited levels of surface finish that are available, but you can make parts with almost no geometric limits, so with overhangs and undercut areas and without all the considerations that go into a molded part. We finally transitioned a little while ago to an injection molded rear cap. And I would say it is, it's a little bit more premium. We've added some fine details. We've made it look as good as we possibly can. But it takes hundreds and hundreds and hundreds of these before you get over the initial investment for saying, I would like to mold something. There's a big barrier to entry that 3D printing gets us and a huge number of other small manufacturers away from.
Yeah, if only you knew when you first made these how many units you'd end up shipping.
This is always the thing, and that's the the challenge that you've got is saying, okay, I can make these for, I don't know, if it's $5 a part, and I can start with an investment of $5 to get a part, and that's very straightforward, and it's very attractive. And injection molding, yeah, the first part is $10,005. And yeah, sure, by the time you get thousands of units down the line, they start to cost, instead of $5 a go, they start to cost 15 cents, 20 cents a go. But you've got to, the maths is not on your side to start with. It's a big uphill struggle to get that done. And there are also a lot of limits with injection molding. You have to be very cognizant of draft angles and undercuts, and literally being able to get the part back out of the mold it was made in is not trivial. So we have parts like this little guy here. So this is a housing inside of the strata electro that takes 3 small motors, and it has mounting points for motors, for screws, cooling holes, bearing mounts, things going in every direction.
Yeah, it's a complicated little part.
It's a complicated little part. It's really pretty trivial as a 3D print. That's produced with a resin-based 3D printer in a sort of tough ABS-like material that's pretty healthy and robust. No processing.
That's literally straight out of the printer.
Straight off the printer. And that is also, it's about, again, intelligent approaches to the design. We make sure that we, just like you do for CNC, for injection molding, for die cutting, for laser cutting, you learn what does the process let you do. And in this case, there's a great deal of freedom geometrically, but you have support structures that you need to remove, points that are going to be poor quality because of the attachment of the support structures, orientations that do and don't work. So you learn to work around those things, and some parts, not all, some parts you can design so that they 3D print, they pop off the machine, and they're ready to use. Other times 3D printing can be a world of hurt when it comes to post-processing and trying to make things actually be functional.
Yeah, absolutely.
So it's rare that we have a finished part that's a 3D print. And there are certain things that we do. There's a component here from the inside of the Strata PLND, which is a combination of, for the horological fascinated among us, there's a Geneva wheel mechanism on one side and a tooth belt drive on the other, with room for a machined pin through the centre.
And what you're seeing there is very much the heart of the little mechanism.
Yeah, exactly. It's the part that makes everything possible, really. But that was prohibitive to make to the tolerances that we wanted as a machined part. And yeah, again, 3D printing won out in that instance. Next to no post-processing, job done.
Yeah.
And 3D printing does allow you to do impossible geometry, especially on very small parts. So there's another little internal component we're looking at here. It's sort of unmillable, basically. There's tiny, it gives you the freedom to do all the things that you really shouldn't. Basically, you design for manufacture as far as you possibly can, but 3D printing, in a sense, lets you cheat and try and get away from that.
Yeah.
So yeah, just to round up on that, I'd say a lot of the time, picking a process according to both the scale that you're working at and the budget that you're working to and the tolerances that you need, you do have to pick and choose. And there are always going to be places and times where you need to find a specialist. So there are a lot of generalist people out there as far as machining and creating physical objects are concerned. There are certain things among them, like, if you can see it, the invisible item here. So that is a custom-made pogo
goodness.
pin electrical contact, which has inside it a mechanism and springs and multiple moving parts.
Yeah.
There's no good giving an engineering drawing for that to somebody who is not experienced with exactly that part. At best, they will tell you to go away. At worst, they might try and do it and charge you a gigantic sum. But for people set up in the right way with the right type of machines, it's trivial.
Yeah.
So we need to try and find the person for whom the question is trivial.
Absolutely. Yeah.
So that you don't just get a yes that lands you in trouble. The main place that we actually see 3D printing used is creating our own tools, jigs, and equipment.
There's so much around the office that I see.
So a sort of a grand example of it here. This is a jig that's used in the assembly of the Strata Electro, which is a multi-part jig that lets you hold the internal components while they're being assembled and cleaned, test them on a test bed, pick them up, handle them, and drop them into place inside the device.
Which otherwise would be a nightmare.
Yeah, exactly. It's the kind of thing you can't touch or handle. But this has, like I say, numerous moving parts, sprung components, things that clip together.
Absolutely.
All of which are, one-offs, two-offs that you need as part of a manufacturing process. I mean, I've heard it said, and I do think it's true, that one of the biggest parts of designing and making anything is designing the tool you need to do it. You're designing the factory.
Especially if you don't want all your employees to walk out the moment you design a new product.
Yeah, that's it. I do worry once in a while that it's really exciting to tell customers, hey, I've got a new idea. And sometimes I feel like other people in the room are like, oh God, he's done it again. This is going to be really hard to make.
Obviously not doing a bad job though, because everybody who started here is still here.
Well, yeah, this is true. Yeah, but yeah, it's great to have stuff that requires skill, because that's the thing that we've got in-house is skilled hands, people who understand what's going on and can do the difficult assembly work. But by the same measure, it's not sensible, profitable. It's not either reliable or serviceable if you make something that is onerous to put together to too much of a degree.
Yes.
We do have some complex little items. Again, there's more stuff from the inside of the Strata here. So, there are 1, 2, 3, 4, 5, 6 components plus 4 bearings involved in this little tiny piece of mechanism. You've got stuff made on a sliding head lathe. You've got stuff made by CNC. You've got stuff cut on a hobbing gear cutter. There's anodizing. There's paint fill. There's, for a tiny component, a sub-component of a system, there's a lot of mechanical processes.
Kind of an assembly.
Yeah, that's it. All the time it's both reliable and satisfying and has all the good stuff attached to it. That's, then it's really enjoyable to turn that kind of stuff out.
Absolutely.
And the fun, probably, I think one of those fun things, and I know people enjoy this on the customer side as well, is surface finish stuff. When you get past just we're going to make this and it's got to work, you start to get into, okay, well, now it works. What can we make it look like? What can the surface finish be?
It's brilliant.
And aluminium is a lovely material to work in for that. A few little examples here. Aluminium takes a polish nicely, it takes a bead blast nicely, it'll take sulfuric anodize or hard anodize, be dyed in a number of different colors. It's fun, and we don't really necessarily publicize it a lot, but I know that people will often say, hey, can I have this in a different color, to match their brand, to match their production. And actually it's much more art than science, producing these kinds of things in the right color. But we're fortunate to have partners who are good at the art. We don't have to swear at them too many times to get the bespoke results that we're after.
Absolutely.
And yeah, it's incredibly satisfying to take a starting point of a part that is beautiful but functional, and see it come back in a finished form, and then take its engraved markings, its paint fill, and become a finished item.
Yeah.
It's super satisfying.
Absolutely.
So that's literally all I wanted to do, is just have a quick chat and a rundown on some manufacturing stuff. Feel free to post questions that you have in the comments. I know it's not easy for everyone to join us literally live on these things, but I know we've been getting some nice feedback from people watching it back afterwards. I will be checking in on comments there and see if there's either suggestions for more stuff you want to hear, anything we can answer, and we'll look forward to seeing you all again next time. I think we're going to be talking about secret new things next time. If that's enough of a tease for you.
It's not all about electro.
Yeah, exactly. Awesome. I'll see you again soon.